Welcome to this explainer. We constantly see AI processing visual data at absolutely breakneck speeds, but today, relying entirely on a fantastic breakdown from Amon's AI journal, we're going to look under the hood to see exactly how it pulls this off.
But hey, before we jump right onto the assembly line, let's lay down our baseline. A convolutional neural network, or CNN, is basically deep learning's premier tool for visual data. It's a specialized algorithm built entirely from the ground up just to handle images. And the crucial takeaway here is that it doesn't just memorize a picture, it actively learns hierarchical representations to extract the features that actually matter. Because we are looking at a highly structured process today, we'll follow this roadmap. We're going to track a single image through decoding visual data, moving from pixels to matrices, finding the features, shrinking the map, and finally getting to that final classification.
To make this whole thing even easier to digest, try thinking of the architecture like a literal assembly line, grouped into three main phases: ingestion, refining the signal through pooling and nonlinearity, and ultimately reasoning and prediction.
All right, let's start with Section 1, decoding visual data and the real challenge of machine vision.
See, to get a machine to actually understand an image, it has to extract meaningful features completely from scratch. It does this by learning hierarchical patterns. What this really means is that a computer doesn't just look at a whole picture and instantly get it like our human brains do. It literally has to build an understanding from the bottom up, step by step, to achieve that impressive accuracy in classification.
Moving right along to our first station on the assembly line, pixels to matrices. This is our ingestion phase.
What's really alien to us here, and frankly, kind of proves computers have zero appreciation for art, is that an image enters the CNN not as a beautiful, colorful picture, but brutally stripped down into a massive matrix of numbers. Every single pixel is represented by three distinct values for red, green, and blue.
And those color values, they strictly range from 0, representing pure black, all the way up to 255, which is pure white. It's a massive, dramatic transformation. The computer takes a vibrant photograph and translates it into pure, unadulterated math. That giant matrix of numbers is literally the only thing the CNN sees at this stage.
Okay, so with our image completely shredded into numbers, we enter the next highly active phase, finding the features using convolution and nonlinearity.
This is where the convolutional layers get to work. Picture these layers acting like scanners. They apply mathematical filters, sometimes called kernels, across that massive grid of numbers. By sliding these filters over the data, the network starts to identify basic geometry. We're talking simple edges, straight lines, and basic textures. And the result of all this scanning? It creates what's known as a feature map.
Next up, that signal hits the ReLU layer. That stands for Rectified Linear Unit. It takes that feature map and applies a pretty ruthless mathematical filter, max of 0 and x. Simply put, if a number is negative, boom, it zeroes it out. If it's positive, it stays. This brilliantly filters out all the noise and increases the CNN model's nonlinearity, which basically makes the important features pop out much more sharply.
So our feature map right now is mathematically massive, which brings us to stage 4, shrinking the map through dimensionality reduction.
We just have way too much data. So the pooling layers step in. Their entire job is to efficiently compress this massive amount of numerical data. They reduce the dimensionality of the feature map, but they do it very, very carefully. The goal is to shrink the file size, so to speak, while strictly retaining those essential visual clues the convolutional layers just found.
Let's look at a technique called max pooling. It does exactly what it sounds like, actually. It scans a small, filter-covered section of that feature map and literally just grabs the maximum value within that section, tossing the rest. It's ruthless, for sure, but it's a highly effective way to efficiently shrink the map without losing the core prominent features the network detected.
But this leaves us with a fascinating puzzle, right? We have all these isolated edges, lines, and shrunken feature maps floating around. How does the AI actually connect all these isolated mathematical dots to make a final prediction about what the image is?
That question brings us to the climax of our assembly line, the final classification.
Now this is where the magic really happens. We finally transition from just extracting basic features to engaging in actual high-level reasoning. This takes place in the fully connected layers. Here, the neurons wire together, connecting to literally all the activations from the previous pooling layer. It takes all those shrunken, isolated edges and textures and looks at how they combine, piecing the puzzle together to recognize the larger hierarchical pattern. Once the reasoning is done, the output layer has to deliver the result using specific mathematical functions. It uses a function called softmax if there are multiple possible categories it needs to choose between. Or if it's just a simple binary choice, like yes or no, cat or dog, it uses the sigmoid function.
Ultimately, it all just comes down to the numbers. The class that scores the highest probability is officially declared the CNN's final prediction. That highest number becomes absolute truth for the AI, completing this incredible journey from a raw matrix of red, green, and blue pixels to a concrete, reasoned classification result.
It really leaves you pondering, doesn't it? If a machine can achieve such staggering accuracy by simply turning our rich visual world into a matrix of numbers from 0 to 255 and running them down an assembly line of filters and pools, what else around us could we decode? What other complex parts of human reality are just waiting to be translated into a feature map? Thanks for joining me on this explainer. Keep learning, and I'll catch you on the next one.